welcome back to this lecture. In the last lecture, we were discussing about how real time tasks can share resources. Initially, we had looked at the priority inheritance protocol, which is a very simple scheme, where a lower priority task which has acquired a resource inherits the priority of a higher priority task waiting for the resource. But then the basic priority inheritance scheme had two major problems. One is that it does nothing to avoid deadlocks, and the second is the chain blocking problem, where a higher priority task needing multiple resources undergoes inversion for each of the resources. We looked at improvement over the basic priority inheritance scheme known as the highest locker protocol. In the highest locker protocol, ceiling priorities are assigned to resources depending on what is the highest priority task that may use that resource. And once a task acquires the resource, its priority is increased to be equal to the ceiling value, and therefore, other tasks which do not need the resource, but are of higher priority, they get blocked, and that is called as inheritance blocking. And this is a major problem with the highest locker protocol, and in today's lecture, we will quickly complete our discussion on the highest locker protocol, and we will discuss the priority ceiling protocol. In the highest locker protocol, let us look at some of the properties of this protocol. When a task gets one of its resource, it is not blocked any further. What it means is that under the highest locker protocol, chain blocking cannot occur. Why is that? How can we argue? A formal proof is given in the textbook, but then informally we can understand that when a task acquires a resource, its priority increases to be equal to the highest priority that may use the resource. And therefore, if any of the resource that is used by a task is already acquired by another task, then that task would have higher priority and the current task would not be allowed to run. Let me repeat again that let us say a task needs two resources, R1 and R2. The ceiling value associated with those two resources must be equal to or greater than the task that we are considering. And let us assume that one of the tasks is locked by one of the resources is locked by another task, or both the resources are locked by other task, and then let us assume that this task requires the first resource, and then it blocks until the first resource is freed. But then the task holding the second resource, its priority does not drop below the task waiting for the resource, because the resource ceiling value must be greater than the task that is requesting the resource. Therefore, it is easy to see that under highest locker protocol, chain blocking cannot occur, and therefore, before a task is granted one resource, all resources that it requests must be free, and it cannot undergo chain blocking in the highest locker protocol. Now, let us look at its behavior with respect to deadlock. Let us assume that task T1 and T2 have the a similar sequence of events as occurred in the case of simple priority inheritance scheme, where we showed that deadlock occurs. Here let us assume a similar set of instructions. Let us assume T2 is the lower priority, it locks R2, but once it locks R2, the priority of T2 gets increased at least to equal to T1, and therefore, T1 cannot become ready, cannot get CPU to lock R1, and therefore, T2 priority is increased to at least that of T1, and it locks R2, R1, then unlocks R1, R2, etcetera. So, deadlock cannot occur. You can take any other example and see that deadlock cannot occur, because T2's priority is made equal to the ceiling priority of the resource it locks, and if the other task needs the resource, its priority will be as much as the priority of the other task. And also it prevents unbounded priority inversion, because the task's priority as soon as it acquires the resource increased to a high value, which is the ceiling of the resource. But as we have already discussed, that the major shortcoming of the highest locker protocol is the inheritance blocking. Since the priority value of a low priority task as soon as it acquires a resource is raised to a high value, the other intermediate priority tasks which do not need the resource undergo inheritance blocking, and the intermediate priority tasks can miss their deadline, because for multiple lower priority tasks they may face inversions, priority inversions, and they may miss their deadline. Let us look at the blocking time for a task. Let us assume that uses S is the set of all tasks that use the non preemptible resource S, and TKS, CTKS is the computation time using the resource S for the task Tk. Therefore, any task Ti can be blocked to the maximum time, which is the maximum of Tk using the S, and Tk is in uses S. What it really means is that, for if we are trying to compute what is the maximum blocking time for a task Ti, which does not need the resource, we find all the lower priority tasks. So, that is Pk, priority of k, that is all lower priority tasks, and we find that what are the resources it uses, and then find what is the maximum computation time using the resource. For all the lower priority tasks, what is the resources they use and what is the maximum time they use, and that is the blocking time for the task I. The highest locker protocol is used in many operating systems. For example, the POSIX standard, there we have the priority locking mutex, where we have this set priority to p thread prio protect. The prio protect basically is the highest locker protocol. So, it is supported by POSIX. Linux does not support highest locker protocol, but ADA programming language supports highest locker protocol. Even the real time specification for Java supports highest locker protocol, though it calls it as the priority ceiling emulation. The inheritance related priority inversion, as we have already mentioned, is a severe problem. Tasks not needing the resource, the intermediate priority task, undergo inversion, and the priority ceiling protocol overcomes this drawback to a large extent. By this time, I hope that we have understood what are the drawbacks of the basic priority inheritance scheme and also the highest locker protocol. Now, let us look at the priority ceiling protocol, which is a improvement over the highest locker protocol, and most of the sophisticated real time operating systems use the priority ceiling protocol or PCP. Very simple operating systems do not use PCP, because the scheme is slightly more complicated than the basic priority inheritance scheme and the highest locker scheme. Now, let us see the main idea here. Just like the highest locker protocol, each resource is assigned a priority ceiling, and the main difference with respect to the highest locker protocol is that a task's priority does not become equal to the ceiling priority of the resource as soon as it acquires a resource, but here it is only a system variable. The value becomes equal to the ceiling value. The task's priority upon acquiring a resource does not change, but only a variable, a system variable whose name is current system ceiling, the value of that increases. Let us look at this example. If R is a non-preemptible resource being used by 3 tasks T10, T2 and T5, then the ceiling value associated with R is equal to T2, and any task which acquires the resource, the task's priority does not increase. Unlike the highest locker protocol, it continues with the same priority, but then there is a operating system variable whose value becomes 2 when any of the task acquires the resource. To look at the difference between the priority inheritance protocol and the priority ceiling protocol, the priority inheritance protocol is a greedy approach. Whenever a task requires a resource, it gets it if the resource is free. But in the priority ceiling protocol, we will see that even if a resource is available, a task executing requesting that resource may not get it under some circumstances. So, we can say that priority ceiling protocol is not a greedy approach, in contrast to the priority inheritance protocol, which is a greedy approach. Now, let us look at the current system ceiling. This is a operating system variable, and whenever a task acquires a resource, the task's priority does not increase. It is only the current system ceiling which gets the value of the maximum ceiling of all the resources that are being used. So, if CRI is the set of resources that are currently being used, then the ceiling of the CRI, maximum of that, becomes the CSC. If there are 2 resources, let us say CR1 and CR2, the ceiling value of CR1 is 5 and the ceiling value of CR2 is, let us say 2, and 2 is higher priority, then if both resources are becoming used, then CSC will be set to 2. At the start of the system, the CSC is initialized to 0. Now, let us see how does resource sharing occur under the ceiling protocol. There are actually 2 rules. The first rule applies when a task requests a resource. This is called as the resource request rule. The second rule is called as the request release rule. This rule applies when a task releases a resource. First, let us look at the resource request rule. In the resource request rule, there are two clauses. First is called as the request grant clause, where a task requesting a resource gets the resource. The second is called as the inheritance clause, where a task does not get the resource, but it blocks. Let me repeat again. In the resource grant clause, this clause is applied when a task is granted a resource, whereas a inheritance clause is applied when a task does not get the resource it requested, but it blocks. First, let us look at the request grant clause. Simple clause. Here, once the task gets the resource, then the current system ceiling is checked with the ceiling of the resource it has got, and if the ceiling is greater than the current system ceiling, then the current system ceiling is set to the resource, and the task is not allowed to lock a resource unless its priority becomes greater than CSC. In the resource grant clause, the task's priority is checked with the current system ceiling, and if its priority is greater than the current system ceiling, then it is granted the resource, and the current system ceiling is set to be equal to the ceiling value of the resource that was granted. Let me repeat again, because this is an important clause here. Resource grant clause. When a task requests a resource, first its priority is compared with the current system ceiling, and if its priority is greater than the current system ceiling, it gets the resource, it is granted the resource, and the CSC value is set equal to the ceiling priority of the resource. But if the task requesting the resource priority of the task is less than CSC, it is not granted the resource and it blocks. So, in the resource grant clause, a task requesting a resource, if it is holding a resource whose ceiling priority is equal to CSC, then it is granted access to CR. So, there are two clauses here in the resource grant clause. The first is, if it is priority of the task is greater than the ceiling priority, it is granted the resource, and the current system ceiling become equal to the ceiling associated with the resource. But even if its priority is not greater than the current system ceiling, but then if it is holding any resource whose ceiling priority is equal to the CSC, then also it is granted access to CR. Otherwise, it is not granted access to the resource and it blocks. And as I was saying, that as soon as a task is granted the critical resource, the current system ceiling is made equal to the ceiling of the resource that is granted, if the ceiling of the resource is greater than the current system ceiling. Now, let us look at the inheritance clause. If a task is made to block, it is not granted the resource, then the task holding that resource inherits the priority of the blocked resource. Let me repeat again. If a task blocks for a resource, then the task holding the resource inherits the priority of the blocked task. A task that has holding a resource does not change its priority, unlike the highest locker protocol, but only when a task blocks for a resource, it inherits the priority of the task. Now, let us look at the resource release rule. It is just the reverse of the resource grant rule. Here, as soon as a task releases the resource, the CSC is again checked with all the tasks that are under all the resources that are under use, and the ceiling is set to the maximum of that. But if the current system ceiling is equal to the ceiling of the current the task the resource that is released, then the CSC remains unchanged. Let me repeat again, the current system ceiling, as you know, it is the maximum of the ceiling of the resources under use. If a resource is returned and that is equal to the CSC, then all the resources are checked, their ceiling values obtained, and the maximum of that ceiling value is assigned to the CSC. But if the ceiling value of the current resource is less than CSC, then CSC remains unchanged. And also the priority of T1 is updated. If it is released a resource, then any task that was blocking on that resource, it might have inherited the priority. So, the task's priority in that case is reverted back to the original priority. Let us look at the working of the ceiling protocol with some examples. This is a resource, critical resource being used by 3 tasks T1, T2, T3. Priority of T1 is 10, priority of T2 is 2, and priority of T3 is 5. And since 3 tasks can use CR1, the ceiling priority associated with CR1 is 10, assuming that 10 is the highest priority, just like in a window based system. To start with, the current system ceiling is set to 0, and let us assume that T3 locks CR1. T3's priority does not change, unlike the highest locker protocol, it continues with 5 priority. But then the current system ceiling is equal to the ceiling priority of CR1, which is equal to 10. So, the CSC value only increases. And let us say next time another task requests a resource, it is the task T2 whose priority is 2 has acquired the resource, and the current system ceiling is set to 10, and now let us say there is a task T3 which is executing, because T2's priority does not change, it continues to operate at the priority level 2, and let us say a priority 5 task T3 executes, and after some time it requests T2, and in that case the inheritance clause will apply, and the priority of T2 will become 5, and as soon as it releases the resource, the release clause will apply, and it gets back its older priority of 2, and the current system ceiling is still 10, because T3 is being using CR. So, the ceiling priority of the resource is assigned to the current system ceiling, and let us say T4 is another task which is needing a different resource CR2. It will not be allowed to lock this resource, because the priority of T4 will compare to the CSC, which is 10, even though the priority of T4 is 6, which is greater than T3, but then it is requesting a resource which is idle CR2, it will not be granted, because in the priority grant clause the priority of T4 will be compared to the current system ceiling, and since the current system ceiling is more than the priority T4, T4 will not be allowed to lock the resource. So, let us examine the priority ceiling protocol, what really happened when a task is granted a resource. Its priority actually does not change, only the current system ceiling changes. Unlike the highest Locker protocol, the task continues to execute at its own priority. So, other tasks which do not need resource, they do not get blocked. Unlike the highest Locker protocol, where blocking by a task just because a lower priority task has acquired a resource does not occur, and that we had called as inheritance related inversion. The inheritance related inversion in that sense does not occur here, because as soon as a task acquires a resource, its priority value does not change. The other tasks continue to execute as usual, no inheritance related blocking occurs. The priority of task changes only when another task requests the resource that it is holding. The inheritance clause becomes applicable and the task priority increases. If we analyze the priority ceiling protocol, we will see that it prevents deadlocks, prevents chain blocking, prevents unbounded priority inversion, and also limits the inheritance related inversion. The inheritance related inversion is a big problem with the highest Locker protocol, and that is reduced to a large extent by the priority ceiling protocol, and therefore, priority ceiling protocol, though it is a slightly more complicated protocol than highest Locker protocol, but is being used in many applications. Now, let us do a small analysis of the priority inversions that can occur in the ceiling protocol, priority ceiling protocol. If we look at the different types of priority inversions that can occur in the priority ceiling protocol, we will have three types of inversion. One is called as direct inversion, the other is inheritance related inversion, and the third we call as avoidance related inversion. The direct inversion is simple. Here, when a lower priority task is holding a resource, a higher priority task has to wait until the lower priority task releases the resource. Let me repeat again that in a direct inversion, a lower priority task is holding a resource, the higher priority task has to wait. A higher priority task needing that resource has to wait until the lower priority task completes its usage of the resource and releases it. Now, this is a small exercise here. There are 6 tasks, and in this task graph, what are the resources, critical resources each task needs, and what is the duration for which it needs has been represented. T1 and T2 need R1, T1 needs it for 5 units, T2 needs for 2 units, R3 is needed by T2 and T6, and R2 is needed by T1 and T4 for 1 and 5 unit respectively. Now, please identify the direct inversions that can occur and assume that the tasks have been sorted in terms of their priority values, that is T1 is the highest priority and T6 is the lowest priority. The direct inversion can occur in case the T2 is holding R1, T1 has to wait even though T1 is a higher priority, and the time for which T1 has to wait is 2 on account of R1 and T2. Similarly, T2 has to undergo inversion, direct inversion on account of T6 and resource R3 for a duration of 8. Similarly, T1 may in the worst case undergo 5 units of inversion on account of T4. I hope that the direct inversion is clear, that a higher priority task will undergo direct inversion on account of a lower priority task holding the resource. We are just running out of time for this lecture. We will stop here and we will look at the other types of inversions that can occur in the priority ceiling protocol in the next lecture. Thank you.